Hello, and welcome to this Global Positioning System training session. We will present the system as a whole, as well as ST's GPS chipsets. Let's start from the original need: measuring distance. Measuring the distance between two objects by electromagnetic waves was first implemented in radar systems. A radar system has one unit transmitting the signal and receiving the reflection from the other object. GPS, on the contrary, has satellites orbiting the Earth and sending signals to any receiver in direct view of the satellite. The time the electromagnetic wave takes from the satellite to the receiver on the Earth is directly proportional to the distance between the satellite and the receiver. However, with one satellite, you can only measure the distance, but you cannot determine the position. This is because the signal from the satellite can be received at many points on the Earth at the same distance, forming a circle on the Earth's surface. This means you cannot know exactly where you are. If we use a second satellite, we can measure the distance between our position and satellites 1 and 2 at the same time. Each satellite provides an equidistant circle on the Earth's surface, and the two circles cross at 2 points. This limits our position to one of 2 points. For a rough estimate, this is sufficient, because you normally know if you are at point 1 or point 2. However, to be absolutely sure of where you are, and we are talking about a few meters, this is not sufficient. We need another satellite. The third satellite gives you another equidistant circle, and there is only one point now where the 3 circles cross. With 3 satellites, you thus have the possibility of calculating your exact position on the Earth. But these 3 satellites are not standing still. They are continually moving. Since the satellites are not stationary, but orbiting in an equatorial plane one after the other, this makes the calculation of the position very difficult. Furthermore, they are only visible for a while. Then they disappear behind the horizon. To get around this, the GPS system uses at least 24 satellites orbiting in 6 different orbital planes. The angle between these different orbital planes is 60 degrees, while the orbits have an inclination of 55 degrees relative to the Earth's rotational axis. The orbiting time of a satellite is roughly 12 hours, with the satellites periodically disappearing and reappearing. At any time, you can see at least 8 of the satellites from the Earth's surface. Each satellite has 2 atomic clocks, which are very precise. They are controlled and synchronized by the ground stations for long-term accuracy. The satellite's times are transmitted with the signal. Receivers, on the other hand, have a very inaccurate time measurement compared to this. The error in the time difference between the satellite transmission time and the receiver's time at arrival gives a position error, which ranges from several hundred to several thousand meters. Inaccuracy in the receiver time alters the ideal circular line of equal distance to a circular area of pseudo distances. When using 3 satellites, the equations do not match, and there is no unique point, but a spread of intersections. If we synchronize the 2 clocks, for both the satellite and the receiver, the equations again have a unique solution. To synchronize the clocks, we need a 4th satellite. With 4 satellites, we now have 4 equations that give us a unique solution for the correct position in space, x, y, z, and time. We can thus synchronize the receiver clock with the satellites and the GPS time, which are the reference. Now, what do satellites transmit? This is a typical block diagram of the satellite signal architecture. We start from a precise 10.23 MHz frequency. This frequency is multiplied using a PLL, or phase-locked loop, with a factor of 154, which gives you the satellite's carrier frequency of 1.575 GHz for GPS used for civilian usage. Then we have the PRN CA code. This is a 1023-bit code, which repeats periodically and is transmitted on a 1.023 MHz wave. This frequency is generated from the 10.23 MHz by dividing by 10. The third frequency we use is a 50 Hz clock, which is generated by dividing the 10.23 MHz by 204,600. The 50 Hz clock is used to transmit the satellite data. There is another frequency used for the PRNP code. This is for military use only, so it does not concern our receiver systems. The system uses phase-shifted keying modulation. There are two multipliers or mixers which use the frequency carriers either directly, I, or with a 90-degree shift, Q. Concerning the PRN code, each satellite uses a unique pseudo-random number of 1023 bits. Pseudo-random numbers are generated in electronic systems using a shift register with some feedback paths. The input of the shift register is determined by the feedback paths logically combined using an XOR gate. Depending on the keys used for the feedback paths, different unit numbers can be generated. Clocking the shift registers, we get a unique digital code, which in the case of GPS repeats every 1023 clocks. Each of these bits is called a code chip of the PRN code. Note that these are not data bits, as they are always the same for the same satellite. However, the reality is even more complicated than this. The satellites and receiver circuitry to generate the CIA-PRN codes consist of two 10-bit shift registers, a fixed one and a programmable one. In the receiver system, the PRN codes may be set by writing to a register. In this way, you can determine which satellites you are going to track. The PRN codes are called gold codes and are very different from the others, so preventing any cross-correlations. Let's see what the PRN code is used for. First of all, the PRN code determines the specific satellite you are looking for. Then, it is used to generate a spread spectrum modulation. A sinusoidal signal has a spectrum of a single frequency. If you modulate this with a second frequency, you get the carrier and the carrier plus and minus the modulating frequency. If you use a rectangular signal to modulate the carrier, you get all the odd overtones of the signal or the modulating frequency. So you get these troughs or sidebands beneath the carrier. Using a random digital number or PRN with 1.023 MHz to modulate the carrier, shown in the fourth diagram here, and PSK modulation, the signal spectrum is distributed over a frequency band of plus or minus 1 MHz with very low energy content. GPS uses spread spectrum modulation. How can we find the satellite from the receiver? It is a matter of correlation. The signal received from the satellite is fed to a correlator on our GPS-baseband devices, SAT-PRN. A defined PRN code, which we generate in our receiver, is provided to the correlator as well. As you can see, if we compare these two signals, they do not match, as they are different. The red background shows where the signals do not match. When the satellite signal and receiver PRN code are identical and in phase, the XOR output becomes a straight line. This indicates that the satellite with this PRN number is present. The satellite system sends stable signals, repeating the PRN code every 1.023 milliseconds. The receiver generates the PRN sequence starting with a different phase from the PRN code, so the signals do not match. To find a correlation, you have to move the generated code in time up to the point where it matches the receiver signal. Shifting the PRN code in the receiver to find a satellite is part of the acquisition task. In parallel with the PRN code, the satellite also transmits data. How is this data modulated onto the carrier? If the data bit to be sent is a logical 0, we use the PRN code itself. If the data bit is a logical 1, we simply invert the PRN code. Note that in the diagram we have represented 25 code chips for one data bit. In reality, the GPS signal uses 20,260 PRN code chips for one data bit, because we just have 50 Hz transmission rate for the data. What does a data frame look like? GPS works with 30-bit data words. 24 bits are data bits, and 6 bits are the parity calculated over the 24 data bits. 10 of these 30-bit words make up a subframe, and 5 of these subframes make up a data frame. The data frames are transmitted sequentially over and over, requiring 30 seconds per frame. The subframes contain different types of data. Subframes 1, 2, and 3 always contain the same data, while subframes 4 and 5 contain different data during the repetition of 25 sequential frames. This allows more data to be transmitted on these 2 subframes, but it takes much longer, 12.5 minutes to be precise. The 10 words within a subframe contain specific data, whereas word 0 is always the TLM, which contains specific data, and word 1, called how, contains the time of the week. If we come back to the signal, the satellites are orbiting at a height of 20,183 kilometers. The signal transmitted by the GPS satellites for the CA code, for example, is just sent with 21.9 watts. Traveling all the way down to Earth, the signal is attenuated, and we receive about minus 160 dB watts. At the same time, electromagnetic radiation is the cause of a certain background noise. This noise is generated by solar effects and other electromagnetic signals from various radiation sources. If a signal is lower than this background noise, you cannot see it, and you cannot really recover it. The GPS system can work down to about minus 160 dB watts. There is a very small gap between the background noise and the signal level. If you look at the carrier, the 1.5 GHz GPS signal, it has to be in the range of 30 to 40 dB higher than the noise to be detected, satellite acquisition, and about 12 to 19 dB to be tracked, followed when detected. This value is called CN0, the carrier-to-noise ratio. Let's look at ST Microelectronics' GPS receiver architecture. First of all, we have an antenna, which is usually a patch antenna, usually a ceramic plate with metallized surfaces similar to a printed circuit board. The size of the patch antenna can vary and is normally in the range of 2 by 2 centimeters or 3 by 3 centimeters. The signal from this antenna is amplified by a low-noise amplifier, such as the SMA-661, followed by a radio receiver system, as we have to receive a 1.575 GHz signal. The receiver or radio frequency circuit converts the satellite signal down to a frequency band which can be used by the baseband circuit. The digital signal is forwarded to the baseband circuit, which contains all the correlators, PRN generators, and logic to decode the satellite signal. The baseband device also contains a powerful CPU to calculate the equations introduced and determine the actual position in a longitude-latitude system. GPS front-end systems, such as the STA5620 or STA5630, work with a single downconversion. The 1.57542 GHz satellite signal coming from the low-noise amplifier enters the signal path at the RF input. The local oscillator generates a 1.571328 GHz frequency. The difference in the 1.57542 GHz signal produced in the mixer stage results in the intermediate frequency of 4.092 MHz. The RF circuit contains bandpass filters with plus or minus 1 MHz bandwidth. To adjust the optimal signal level, an automatic gain control amplifier can amplify the signal in a range of 0 to 55 dB. At the end of the signal chain, an analog to digital converter produces a digital output. We have 2 bits at the output of this system. Data is transmitted using the 16.368 MHz clock, which is provided by a temperature-compensated crystal oscillator. The front end can be controlled using an SPI interface. In the baseband, the signal enters multiple correlator channel. For the acquisition of new satellites just appearing over the horizon, there is a dedicated DSP that does this acquisition task. This task always runs in the background and always looks for new satellites. When a satellite is found, it is handed over to the tracking task using the satellite for the position calculation. This is done by the 32-bit microprocessor. The output of the system is usually a serial data stream transmitted via a serial interface such as UART, SPI, or CAN. The data stream is formatted usually in NMEA 0183 protocol. ST Microelectronics baseband devices have a CAN controller, so in automotive systems, the device is able to immediately transmit the position in the car network to other systems that may need it. One channel of a baseband device is made up of several correlators. There might be 2, 3, or more, only depending on the physical implementation. A channel also has a pseudo random number generator that feeds the correlators with the PRN code. A numerically controlled oscillator is used to make it advance the clock steps during the correlation cycle, which can be controlled by software to move the phase of the PRN code. A frequency converter and an accumulator stage complete the channel logic. Each channel delivers the raw data to calculate the distance to the tracked satellite and the satellite data that is extracted from the signal. Systems such as Tessio have 16 of these channels in parallel. In the latest systems, such as Tessio 2, we have 32 channels with 5 correlators, which can be used in parallel. GPS is limited to some basic timing. We have seen the transmission rates and the signal protocols from the satellites. If we are starting the system, it takes 30 seconds to download the satellite data for the ephemeris data. Downloading the almanac from a satellite takes 12.5 minutes. If we do not have the almanac data, it is called an autonomous start, and worst case, it takes up to 25 minutes to receive the 25 frames twice if we missed one bit. In real life, this does not happen very often, as the almanac data is valid for several days and is stored in the system. Assuming the almanac data and the time are available, the system only needs to download the ephemeris data. This is called a warm start. The time to first fix for a warm start is in the range of 30 to 40 seconds. Also, for this case, there is a workaround called assisted GPS. This piece of software calculates the ephemeris data containing the satellite orbit information for each specific satellite for some days in advance, and stores it in the system for immediate use. ST Microelectronics provides a GPS library with the chipsets. This library contains all the necessary software functions to calculate a position and can be used within a customer software application. Assisted GPS reduces a cold start to some seconds running an additional software task. Alternatively, the almanac and ephemeris data can be loaded into the system from any system outside. This eliminates the download time from the satellites. Another software add-on offered by ST Microelectronics is the WAAS EGNOS Satellite Augmentation System. These two systems, WAAS for North America and EGNOS for Europe, provide information about the ionosphere data and transmit the data by geostationary satellites. They are not used for position calculation. They only provide the data on how the ionosphere disturbs the measurement. Another add-on that can improve the position accuracy is dead reckoning. This software uses additional sensors such as gyroscopes and speed signals to calculate in parallel with the GPS system the best position. When satellites are obscured and cannot be used for positioning, the system can still keep track of the position changes in tunnels or multi-level parking lots, for instance. ST Microelectronics owns all property rights. Hardware design, intellectual property of the GPS blocks, software, manufacturing, and testing are owned by ST. GNSS systems are also developed internally. Every chipset is qualified according to AEC Q100 for use in automotive applications. ST has recently launched the new Tessio 2 family of GNSS receivers for GLONASS, QZSS, and Galileo systems. You can find more information at www.st.com/GPS. Thank you for your attention.